In a previous video, we discussed the force on a wire in a magnetic field by virtue of the relation that force is current times length in the direction of wire in a magnetic field. We saw that wires can move. They can be pushed up, down, left, right, depending on the orientation of these things, and the force is very apparent and very strong. So it turns out if you use this sort of in a clever way, you can develop what you would probably commonly know as an electric motor. Let's take a look how one of those might work. So what I'd like to do with an electric motor then is the drawing of this thing is kind of difficult here, but we'll try to get it across and change perspectives a few times. So suppose we had a nice big magnet like this with north and south poles, and a magnetic field exists between these poles like this. So there's a magnetic field direction. So suppose then what you did next is you took something like a loop of wire, a square loop of wire, say, for the sake of the illustration, and you stuck it inside the poles of that magnet. So here's where the drawing already gets to be a bit difficult, but let's see if we can maybe add a bit of three-dimensional perspective to the whole thing. Maybe that'll help. So here's sort of the poles of the magnet again here in 3D, and of course that means there's going to be more magnetic field lines sort of all around like this. More magnetic field lines all in there. So the magnetic field, of course, fills the region between the magnetic poles there. Let's try and get that loop in there now. So the loop that we're going to stick in there looks like this. Looks just like this. And then instead of closing the loop right there, I'm actually going to come out with a couple of leads like this that will allow me to turn a current on in there. So if I run a current into this side right here, of course the current's going to go up here, up that way, over this way, down the back there, back the bottom, and then back out here. That's the way the current will flow around. So what you see here is I actually have 4 wires, ignoring this little gap right here. I actually have 4 wires inside of a magnetic field. But this is where actually I'm going to stop this drawing here because it just gets too hard to describe. And what I'm going to do now is I'm going to look at the whole thing end on in the magnetic field. But just imagine that we did that. And I guess furthermore, one more thing. Not sure exactly how one would do this, but suppose that this whole loop here was also very delicately balanced on an axis, so if it wanted to, it could rotate about the axis and sort of maintain its shape and position. Okay, so with that, we're going to get rid of the drawing now and go to a figure that more looks like this. Suppose that I got in there to the region where that magnetic field existed, and I just sort of got in there like this. So here's the magnetic field coming straight out at us, and suppose that I put that loop inside the magnetic field like this. So here's that loop, there's a little gap in there like this, and here's the 2 leads coming out. So that's the loop that I put inside the magnetic field now. Okay? And I don't know if I'm preserving the exact orientation that I had before, but obviously if I can pipe in some current on that input lead right here, it'll go around the loop like that. So that all looks fine. And now what I'd like to do simply is just figure out what are the forces on each one of these segments here, the forces. Okay? So how about down here? Well, I know that my force line is IL cross B. That doesn't change on the wires just because I'm in the loop now. So I'll put this arrow in the direction of I. I'll put the magnetic field coming straight out at you like this. And so if you look very carefully, the result of the cross product, IL cross B, the cross product is this third vector, which is straight down. So this bottom segment here is going to experience a downwards force like this, down like that. There's an F. Okay? How about this side over here, IL cross B again. Here's I, here's IL. B is straight up like that, and it looks like the result of the cross product is over. Remember, B is always the magnetic field, so it's going to be straight up. So there's going to be another force on this wire over that way. Okay, if I just sort of kept going around here, one more IL cross B on the top right here. Here's I, my first vector, IL right there. B is straight up like that, and this popsicle stick is B straight up, so the force on this top wire is going to be along this direction here, which is going to be straight up. There's that force. Okay, and if I sort of keep going, ignoring this small gap here, collectively this whole side here will have a force that way on it like that. So what I have then is 4 force on wires that look like they sort of cancel. But remember the orientation of this loop in here. So I sort of drew it like this for clarity, but remember the orientation of it. This side and this side, this side and this side right here are this side and this side. And so what we have is we have this system here which sort of gets forces up on the top and down on the bottom like that. And let's see, on the sides right here, it's going to be straight out like this and straight out like that. So try to picture that, because what I'm going to do now is I'm going to look at it in still another orientation. So what I'm going to do now is I'm going to imagine that I'm going to look at this object here, the motor or the windings in the magnetic field, sort of straight along this axis right here. Let's just get straight in there and see what that would go like. So here's our our third perspective of the problem here. So what I'm going to look at now is if I do that, I'm just going to lose all perspective on this, but again, it's just sort of hard to draw. Here's the magnetic field. And if I look at this thing again, straight edge on like that, then what I would see is I would just simply see the edge of the wire like this, sort of up like that. Remember, it's allowed to rotate. So this, let me even draw in green here. This green dot here, here's the magnetic field, and this brown edge here is meant to be this brown edge, and so this green dot here is actually this green wire axis here that allows it to rotate. And then let's see if we can get the currents in there now. So what we have here is on this side of the wire here that I've drawn, the current is going up like this. That's the half that sort of feeds it. And then when the current goes up into this top half right here, that's the current going away from us like that. And it travels down that wire. Then it's going to come back along another segment like this, but back in the back I can't draw it now, but then it's going to come back. So as the current comes back along this bottom segment right here, the current's going to be coming at us like that. So I drew the forces on it now. Given that this green dot is a point of rotation, I'll have a force up like that and another force down like that. And so the question before you then is, what is this system going to do? If you have a pivot of axis of rotation right there and an upwards force on the right side and a downwards force on the bottom side, what is this going to do? And if you think it's going to rotate, you'll be exactly right. The system is just going to start rotating like this. It's going to start going around like that. And so what that means then, all told, given the perspectives and all the artwork, some of it very messy and so on and so forth, is that if I put a coil of wire inside of a magnetic field and run a current through it, the system's going to start rotating. And that's exactly what an electric motor is, or does. Is if you take a loop of wire, let's maybe draw what a motor does here. A loop of wire, a B field, and a current in the wire, something like that. What we're going to get here is the loop will spin. The loop is going to spin. Now, in the finished product of an electric motor, what you'd probably actually see is something in a case like this, and sometimes the cases are very heavy, and if you can put paper clips up near the case, they'll stick to it because of the magnets in there, and you'll see a little axis coming out like that, and this axis will turn like that, and then from that you can subsequently connect it to gears or wheels or something, or a fan or something if you're trying to make a fan or something that's going to move. But really what this axis here is this green axis here, which is connected to a loop of wire, which is a magnetic field, that when current is run through it, this is what the force picture is going to look like. You get this imbalance of forces that's going to cause it to rotate like this. Now, a couple of other considerations here. Of course, when the wire becomes vertical like this, when it eventually sort of rotates to this position right here, the current in the bottom is still coming at us, and that current's still coming like that, and the forces will be up like that still. So you might ask, well, is it going to turn still, or is it going to stop? Well, it's going to turn still because, remember, as it starts moving like this, it has sort of a bit of rotational inertia. So it's not like it's going to stop abruptly right here, but its inertia will carry it on through like that. So it'll keep going like that. But then there's some other interesting cases here that might happen, of course, is what happens when, well, let's see, the force on this side will still be up, on this side will still be bottom. What happens when the whole thing rotates all the way down like this so that it gets maybe to this position right here? Let me choose a different color for this so we can see it. What happens when this object rotates all the way around like this, and so when this object here becomes all the way down here so that the current going away from us is down here and the current going towards us is up here? What happens when the whole thing inverts itself like that? Well, what's going to happen, of course, is the force on the top wire now, which is the current coming towards us, is going to be down like this, and the force on the bottom wire is still going to be up like this. See, the force on the wire with the current going away from us is always up, and the force on the wire with the current coming towards us is always down. It's just now that the thing is completely flipped its orientation because it's rotating, and you can see now that where the force on the top wire was once up, now it's down, and where the force on the bottom wire was now down, now it's up. Is this going to stop? Well, actually it would. Well, it wouldn't, it wouldn't. So it would rotate down like this, and by the time it got to this position, the forces are going to be opposite, so it's going to slow down and start going back the other way like this, and stop and slow down. The thing would actually just start sort of oscillating like that, going back and forth, because of the way the forces on those tops and bottom wires reverse direction as a loop inverts itself. So what do you do about that? Well, it's actually a simple mechanical fix. You wouldn't believe sort of what it is, though, is here's the way that loop of wire might look. Here's a little 2 leads that run it like this. And so what you actually do here is you have to picture this whole thing rotating. You would actually connect this top one right here to say the plus voltage for driving the current, and the bottom one here to the minus voltage for drawing the current. But what I really do is use sort of like a different color, or I'll put a couple little arrowheads in here to make it look like this. Because in this region right here, the wires are not attached. So in other words, these arrows here, sort of right in there and right in there, they just drag. They just drag over the loop. So there's a noise in it, like a sound, because these little arrows are dragging over these 2 wires. But you can see what the result is, that when the loop is oriented as shown like this, you'll get a current going in like this and out like that. It'll sort of go around like this and like this. But if this whole loop inverts itself, then suddenly this lower lead wire right here is now connected to the upper terminal, and this upper lead wire is connected to the lower terminal, and that has the effect of reversing the current. So suddenly the arrows are not going to be these black ones anymore, but they're going to be pointing back the other way, like this, like this, like this, and like that. It's going to be pointing the other way. So in that model that I drew that showed the top wire and the forces reversing direction like that, this idea here of reversing the current, what that has the effect of doing here is it keeps the forces in the, we'll just call it here, correct direction for rotation. So by reversing the current like that, it won't allow the force on the top and bottom wire to reverse the directions the way I showed you just a second ago in the video. Go ahead and rewind it to look at that. You can imagine if we reverse the current, then the force would stay in the right direction to keep the thing rotating in the same direction. And what this thing is called up here is, you can sort of look it up here, it's called a split ring commutator. Commutator, OR in there. And that's what keeps these motors, at least DC motors, sort of operating the way they should. But of course, because there's actually rubbing in there, things can wear out, and that eventually spells the end of the life of the motor after a while. But of course, they last a good long time before that happens. So that was the goal of this particular video here, to use a law for an individual wire, IL cross B, and then sort of adapt it to a ring here. Multiple perspectives, a bit hard to grasp and stuff, and there's some dynamics of rotating and keeping forces in the right direction. But all told, you bring that together, you'll have yourself a nice little motor that just spins and spins and spins. And so if you wanted to get an idea of what this looks like, if you get on YouTube and maybe do a search for small motor or hand-built motor or something, what you can actually do is get a magnet like this, or a group of little magnets or something. You just make yourself a little north and a south pole like this, and you just get a big strand of wire like this. And what you can do with the wire is, if you can, form it into a bunch of loops like this. So and maybe you can tie or glue it together so this coil of wire here stays compressed. Now what you can do is, if you put this, maybe the whole thing on a piece of wood like this, and got a paper clip, and bent one paper clip like that, and another paper clip like that. So again, this lower thing here is like a block of wood or something like that. You just set the magnet right on it. And these are paper clips right here because they're metal. And what you do is you take this coil of wire that you made here, and you put it so that you got to strip a little of the insulation off the wire here so it actually makes contact with this paper clip in here. You put the big coil like this, another coil like that. You may have seen these before. So the reason why these paper clips are bent in hooks like this is so it can sort of hold the motor up like that. And then what you do is just come in here with your battery here, like a 9-volt battery, and connect one side of the battery to this paper clip, and the other side of the battery to that paper clip. And if you're sort of lucky, the thing will start to spin. So you have to get this coil of wire here, maybe about, 10 turns or so. Keep it nice and neat. Maybe 10 turns up there, because every turn magnifies the force effect that we were talking about earlier here. Get about 10 turns there, hanging on the paper clip. Get a good current in the battery if your magnetic field is strong enough, and this space here isn't too big. So again, because what this ends up doing here is immerses your coil in a magnetic field, and that's exactly the motor that we were just talking about. It'll just spin and spin and spin. You can see examples of this on YouTube. So there is a way of actually demonstrating the effect of getting a coil of wire in a magnetic field, running a current through it, and off it'll go. Kind of fun to watch. So there you go, electric motors.